The sodium battery the entire industry wrote off as impossible just went into mass production. CATL, the largest battery manufacturer on the planet, launched a cell with no lithium, no cobalt, and a cycle life that should not be achievable at this price point. More than 10,000 full charge cycles. That is roughly 3 times the lifespan of the lithium battery in your car right now. It charges to 80% in 15 minutes. It holds 90% of its capacity at 40 degrees below zero, the temperature where a normal electric vehicle barely functions. And it costs less than a third of what lithium cells cost to produce. None of this is a forecast. It is already happening, and by the end of this video, you will understand exactly how CATL pulled it off and what it means for every battery-powered thing in your life. Subscribe so you do not miss what comes next. There is a 30-year story behind this battery. Right now, as you watch this, there is a lithium battery within arm's reach of you. Your phone, your laptop, maybe your car sitting in the driveway, or the electric scooter, locked to the rack outside your building. Lithium-ion batteries are so completely woven into the fabric of modern life that most people never stop to think about them. They just expect their phone to charge overnight, their laptop to last through a meeting, and their car to get them where they are going. And for 30 years, lithium has delivered on that expectation so reliably that the world essentially stopped questioning it. Before lithium dominated, consumer devices ran on nickel-cadmium batteries, heavy, bulky, and capable of holding a fraction of the energy that lithium could store. The jump to lithium-ion in the early 1990s was not a small upgrade. It was a complete reimagining of what a battery could be. Energy density went up by roughly 3 times compared to what came before. Devices got smaller, lighter, and more powerful all at once. The smartphone would not exist without that shift. Neither would the modern laptop, the wireless earbud, or the electric vehicle as anything other than a novelty. The scale of that transformation is hard to fully appreciate today. In 1991, a single camcorder battery lasted about an hour. By the 2000s, the same weight of lithium was powering phones that stayed on for days. By the 2000s, it was moving cars down the highway for hundreds of kilometers. Each generation of devices pushed battery engineers to extract more from the same chemistry, and each time, lithium delivered. It became the default assumption sitting underneath almost every piece of technology that needed portable power, the invisible foundation of the modern world. Sony launched the first commercial lithium-ion battery in 1991. From that single moment, more than $1 trillion flowed into lithium technology over the following 3 decades. Manufacturing scaled, costs dropped. Automakers designed entire vehicle platforms around it. Governments built clean energy policy on top of it. Grid storage projects staked billion-dollar bets on its continued improvement. The momentum of that investment had a gravity of its own, pulling almost all research attention, almost all engineering talent, and almost all capital in a single direction for 30 years. Here's what tends to happen when something works that well for that long. People stop asking whether something better might exist. They stop funding the alternatives. And when that happens, the cracks in the foundation have a way of quietly getting bigger until they become impossible to ignore. Here is why lithium worked so well, and why that same success planted the problems that are now forcing the entire industry to look somewhere else. Here is why lithium works so well. Inside every battery, you have 2 ends, a positive and a negative, with a liquid in between that carries charged particles back and forth. When you charge a battery, you are pushing those particles from one end to the other and storing them there. When you use the battery, those particles travel back, and that movement generates electricity. The engineering to make that process reliable, safe, and manufacturable at scale took decades. But the chemistry at the core has not changed since the first commercial cell shipped in 1991. In a lithium battery, the charged particles carrying the energy are lithium ions. Lithium sits near the top of the periodic table as one of the lightest metals that exists, and right now that single fact is doing an enormous amount of work inside the device in your pocket. The lighter the particle carrying the charge, the more of them you can pack into a given space, and the more energy you can store for the same weight. More particles per gram, more power per cell, more range per kilogram of battery pack in your car. Lithium also has one of the strongest natural drives to push electricity through a circuit, which means you get more voltage without needing a physically larger cell. Put those two properties together, and you get a chemistry that for 3 decades nothing in the world could seriously challenge. The other half of the equation is graphite, the material that stores lithium ions inside the battery. Think of it as a perfectly stacked deck of cards, layer upon layer of carbon atoms arranged in flat, evenly spaced sheets. When you charge a lithium battery, lithium ions slide cleanly between those layers and sit there. When you discharge it, they slide back out. The spacing between the layers is almost precisely matched to the size of a lithium ion, which means the particles move in and out thousands of times without damaging the structure. That mechanical compatibility between lithium and graphite is a large part of why this chemistry proves so durable across 30 years of continuous refinement. Every generation of engineers pushed that same fundamental pairing harder. Better electrolytes, thinner separators, more precise manufacturing tolerances. The result was a battery that improved in a steady, predictable curve, and for an industry building products years in advance, that predictability was almost as valuable as the energy density itself. But here's the thing about a chemistry that works this reliably for this long. The same properties that made lithium so powerful were quietly creating dangers that nobody in the industry had a strong financial incentive to confront. And those dangers, it turned out, were not small. In 2016, Samsung released the Galaxy Note 7. The reviews were strong, pre-orders were record-breaking, and then, within weeks, the phone started catching fire. In pockets, on planes, on bedside tables while people slept. Airlines banned the device from flights. Samsung pulled the entire product line at a cost of $5 billion, and the Note 7 became one of the most infamous product failures in consumer electronics history. But here's what most people missed. This was not really a Samsung engineering failure. Samsung made specific mistakes in how they designed and assembled that particular battery. But the underlying danger was not something Samsung created. It was sitting quietly inside every lithium battery ever made, in every phone, in every laptop, in every electric vehicle on the road. The liquid inside a lithium battery that carries charged particles between the two electrodes is made from organic solvents. Those solvents are flammable by nature. The materials that are best at moving lithium ions efficiently happen to be the same materials that burn. If a battery overheats, gets punctured, or gets overcharged, that liquid can ignite. And when one cell catches fire, the heat it generates raises the temperature of every cell around it until those ignite too. A chain reaction spreading from cell to cell like dominoes falling inside a sealed box. Engineers call it thermal runaway. Once it starts, there is very little that can stop it. The scale of that problem in the real world today is genuinely startling. In New York City, lithium battery fires have replaced electrical fires as the leading cause of fatal fires across the entire city, not a statistic from a decade ago. That is the documented reality in 2026. The fires are coming primarily from e-bikes and scooters with cheap aftermarket battery packs, but the chemistry creating the danger is identical to the chemistry in every lithium cell, regardless of application or price point. Then there's the cold weather problem. In freezing temperatures, lithium ions stop moving smoothly through the electrolyte and begin depositing themselves on the inner surface of the battery in tiny, jagged metallic spikes. Those spikes grow with each charge cycle. If they grow large enough to bridge the gap between the two electrodes, they create an internal short circuit. That short circuit generates heat very quickly, and heat in a lithium battery, as the Note 7 demonstrated to $5 billion worth of certainty, tends not to end well. Even when the spikes never grow large enough to cause a short, the cold weather performance hit alone is severe. At freezing point, a lithium battery loses between 20 and 40% of its usable range. Not because anything is broken, but simply because of the temperature outside. For someone driving in Canada or Scandinavia on a January morning, that can mean losing 100 kilometers of range before leaving the neighborhood. These problems were known. They were documented in engineering literature for years. Manufacturers built cooling systems and battery management software to work around them. But the core chemistry never changed. And the reason it never changed had nothing to do with science at all. 3 countries, Australia, Chile, and China, control roughly 90% of the world's mined lithium. China alone processes approximately 65% of that raw material into battery-grade form and manufactures around 75% of all lithium-ion batteries on Earth. That means most of the world's electric cars, consumer devices, and grid storage systems run on a supply chain passing through a very small number of places on the map. For governments trying to build genuine energy independence, and for automakers trying to hit price targets that would make electric vehicles accessible to average buyers, that concentration was a structural vulnerability hiding in plain sight. Between 2020 and 2022, the price of lithium carbonate, the key raw material for battery production, increased by a factor of 8. Not 8%. 8 times more expensive in just 2 years. Demand for electric vehicles was accelerating faster than anyone had modeled. Battery factories were scaling up at a pace the raw material supply could not match. Companies that had built their cost projections on lithium at a certain price found themselves operating in a completely different financial reality almost overnight. Battery makers that had locked in long-term supply contracts at peak prices were paying far above the market rate, even as spot prices began to fall. Then in 2023, the market swung hard the other way. Lithium prices crashed by more than 70% in a single year. The surge in demand had pulled forward production capacity that took years to come online, and when it arrived all at once. The commodity that had doubled and doubled again suddenly collapsed. The entire industry had been running multi-year business plans against a raw material that behaved like a speculative stock, completely unpredictable, entirely outside the battery industry's control. The IEA projects that by 2030, 85% of the world's lithium refining will still be concentrated in 3 countries. The supply chain that the clean energy transition depends on is not becoming more distributed over time. It is becoming more concentrated. Every electric vehicle sold, every grid storage project commissioned, every government electrification target announced adds another layer of dependency on a supply chain that the buyers of that energy have almost no leverage over. The world had built the foundation of its clean energy future on top of a raw material that a handful of countries controlled, with prices that could double or collapse based on factors completely outside the battery industry's ability to predict or manage. And yet, despite the fires, despite the cold weather failures, despite the price swings and the geographic concentration, the industry had spent 30 years looking almost exclusively at lithium. The reason why starts with a decision made in the 1960s, and an element so common you probably have it sitting in a shaker on your kitchen counter. Back in the 1960s, before lithium was even on the radar of serious battery researchers, scientists were already working with a different element as the foundation of high-energy rechargeable batteries. That element was sodium. It sits directly below lithium on the periodic table. It behaves in almost exactly the same way chemically. It is one of the most abundant elements on Earth, found in seawater, in rock formations, on every continent, and in the salt next to your stove. The first high-energy rechargeable battery ever built, assembled by the Ford Motor Company in 1966, actually ran on sodium, not lithium. Sodium came first. Sodium. But there was a problem that killed the technology almost before it started. That early sodium battery needed to operate at around 300 degrees Celsius to function. Hot enough to melt lead. Fascinating as a proof of concept. Completely impractical for anything a person might actually use. The temperature requirement alone made it a laboratory curiosity rather than a commercial product, and it stayed that way. Then in 1972, a researcher named Stanley Whittingham figured out how to make a lithium battery work at room temperature. That single breakthrough shifted the direction of almost all the research money in the world. Lithium had a working chemistry at temperatures human beings could live in. Sodium did not. The momentum moved entirely, and it never moved back. Sony launched the first commercial lithium-ion battery in 1991, and from that point forward, more than $1 trillion flowed into lithium technology. Sodium got left behind. Not because researchers proved it was worse, not because the chemistry was fundamentally flawed, because the money was pointing somewhere else. Sodium also carried a specific technical problem nobody could solve. Sodium ions are approximately 35% larger than lithium ions. The graphite that stores lithium so efficiently, those perfectly spaced carbon layers matched almost precisely to a lithium ion, simply could not accommodate sodium. Every time a sodium ion forced its way between those layers, it pushed them apart. The structural damage accumulated with each charge cycle. After a few hundred cycles, the battery degraded beyond usefulness. Against lithium, which was already delivering thousands of reliable cycles, that was a fatal weakness. This single material incompatibility kept sodium out of serious commercial consideration for more than 40 years. The chemistry was abundant, cheap, and free of the geopolitical entanglements that would eventually make lithium so problematic. None of that mattered, because no one could find a material that sodium ions could actually survive in. Until a research team found a completely different kind of carbon, and when they did, everything changed. In the year 2000, a research team in Canada identified a form of carbon that behaved nothing like graphite and turned out to be exactly what sodium needed. They called it hard carbon, where graphite looks like a perfectly stacked deck of cards, flat, ordered, uniform spacing between every layer. Hard carbon looks like those same cards after someone crumpled them, scattered them across a table, and froze them mid-collapse. It is made by heating organic material, plant biomass, agricultural waste, or even simple glucose, to between 1,000 and 1,400 degrees Celsius. Inside a sealed chamber with no oxygen present, the carbon atoms lock into place in a permanently disordered arrangement, full of irregular gaps, curved surfaces, and internal pores of varying sizes. Those irregular gaps turned out to be the answer to the sodium problem. They were large enough and varied enough to accommodate sodium ions comfortably without forcing any structure apart. Sodium could move in and out across thousands of charge cycles without the progressive structural damage that had made graphite incompatible. For the first time, sodium had a host material that could survive the demands of a real battery. Here's the problem nobody talks about until they try to build one commercially. Hard carbon absorbs moisture from the surrounding air almost like a sponge. Even a trace amount of water inside a battery cell reacts with the electrolyte and generates gases. Those gases build pressure. That pressure accelerates degradation and eventually destroys the cell from the inside. In a sealed laboratory environment, manageable. In a battery manufactured at industrial scale and shipped across the world, potentially fatal to the entire commercial proposition. CATL committed approximately $1.5 billion over 10 years to solving exactly this. Their first solution was chemical. They modified the surface of the hard carbon itself, replacing the molecular compounds that naturally attract water with compounds that actively repel it. Their second solution was geometric. They developed manufacturing processes that control the size of the internal pores during production with precision down to the scale of an angstrom, 1/10,000,000th of a meter. Pores too small, and sodium ions cannot enter efficiently. Pores too large, and storage capacity is wasted. Getting that balance exactly right, consistently, across millions of cells produced at industrial scale, took years of sustained engineering work that most companies were not willing to fund. The result of that decade of work is a battery CATL calls the Naxtra, and the numbers it produces would have seemed unbelievable for a sodium battery just a few years ago. The Naxtra delivers 175 watt-hours of energy per kilogram. That puts it in the same performance territory as the lithium iron phosphate batteries currently powering most affordable electric vehicles on the market. In a real car, that translates to more than 500 kilometers on a single charge, with a charge to 80% taking around 15 minutes. These are not laboratory projections. They are production-ready numbers from a battery already being manufactured at scale and heading into vehicles. The cycle life is where the specification stops looking like a battery data sheet and starts looking like something else entirely. The Naxtra exceeds 10,000 full charge and discharge cycles before meaningful degradation. Lithium iron phosphate cells, the longest-lived lithium chemistry in wide commercial use, typically deliver between 3,000 and 4,000 cycles under real-world conditions. The Naxtra's cycle life is roughly 3 times that figure. If you charged it once every single day without exception, that battery would still be performing well after 27 years of daily use. A battery engineered to outlast the car built around it. Cold weather performance is where sodium moves from impressive to genuinely disruptive. The electrolyte inside the Naxtra remains fluid at temperatures as low as -58 degrees Celsius. At -40 degrees, the point where a lithium battery is barely functioning, the Naxtra retains 90% of its full charge capacity. For electric vehicles operating in northern climates, that is not a marginal improvement. It is the difference between a car that works reliably through a Canadian winter and one that loses a third of its range on the coldest morning of the year, when that range matters most. The price difference closes the argument. CATL is producing extra cells at approximately $19 per kilowatt hour. Lithium-ion cells currently cost between $55 and $70 per kilowatt hour. That is not a small gap. And unlike lithium, both sodium and the aluminum used in sodium battery electrodes are globally abundant. The supply chain is not concentrated in 3 countries. Pricing is stable and predictable in a way that lithium's has never been. Here is the honest picture. Sodium-ion batteries have one limitation they are unlikely to fully escape. Because sodium ions are physically larger and heavier than lithium ions, there is a ceiling on how much energy can be packed into a given weight. For electric aviation, where every additional gram costs range and payload, that ceiling matters enormously. For the slim profile of a consumer smartphone, lithium will likely remain the better answer for years to come. But for electric vehicles, for grid storage, for heavy transport operating in cold climates, the categories that will define the next phase of the energy transition, sodium has already crossed the threshold. There is a bigger lesson here worth sitting with before the story ends. The problems with lithium were never hidden. The fire risk was documented in engineering literature for decades. The cold weather degradation was measurable from the first commercial cells. The supply chain concentration was visible to anyone who looked at a map. But when the dominant technology is working well enough and the profits are flowing, industries tend not to look hard for something better. It takes a disruption, a price shock, a supply crisis, a moment where the cost of not changing finally outweighs the comfort of staying the same, to make the alternative visible. That moment arrived in 2022, almost perfectly tracking the point at which lithium prices exploded and the fragility that everyone had quietly accepted became impossible to ignore any longer. What CATL is building toward is not a replacement story. They have already engineered an electric vehicle battery pack that divides its storage into 2 separate zones, one sodium, one lithium, managed by software that decides in real time which chemistry to draw from based on temperature, driving conditions, and current state of charge. Cold outside, and lithium would be struggling. Sodium handles the load, long highway drive needing maximum range. Lithium steps up. Neither chemistry is pushed past its limits. Both are used precisely at the point where they perform best. That is the vision. Not one battery winning and one losing, but 2 chemistries each doing the specific job they were built for. The scale of the moment is worth stating plainly. CATL shipped approximately 122 gigawatt-hours of total battery storage across all of 2025. A single sodium-ion supply contract signed recently represents roughly half of that entire year's output, for a technology that was not in commercial production 12 months before the deal was signed. Meanwhile, in September 2025, Natron Energy, the only American company with real sodium-ion orders in commercial production, shut both its manufacturing facilities and canceled a planned $1.4 billion factory. LG Energy Solution, the South Korean giant supplying Volkswagen and General Motors, did not build its sodium pilot plant in Korea or the United States. It went to China, opening a facility in Nanjing with a materials agreement already in place. The scoreboard, at this moment, is not close. The sodium-ion battery did not appear out of nowhere. It was sitting in research papers and university labs for more than 20 years, waiting for the world to need it badly enough to fund it properly. That moment arrived because lithium made it arrive, by becoming too expensive, too geopolitically concentrated, and too structurally limited to keep ignoring what had been sitting next to it on the periodic table all along. Thanks for watching all the way through. If this kind of story is what you come here for, hit the like button and subscribe so you do not miss what comes next. Turn on notifications to be first when we post. Now I want to hear from you. Do you think sodium-ion batteries will make lithium obsolete in your lifetime? Or does lithium still have enough fight left to hold its ground? Let me know in the comments below.